That's an insanely underestimated physical law. It's literally power behind the tron, but no one knows what it is. Surely a part of physicists. It's a basic tool in crystallography. With its help we could reveal structure of some proteins. It gives us super high reflectance mirrors. Yeah, but those mirrors are quite bad. And at the end I would say it even explains band structure of semiconductors with no quantum mechanics. And today we are speaking about the Bragg's law. Just imagine, there are several ways which are connected by springs. If I touch one, the other will feel it, as I would touch spider's web. They are all mechanically connected. But there is a way to make something really crazy. Really crazy. If I shake one of the ways from the net, the motion will remain isolated. It essentially will touch the neighboring vase, but will not propagate far away. I shake one of the vase from the net, but the net will not shake in response, but they all remain mechanically connected. How it's possible? Being rather fundamental, it's based simply on the wave interference. When there are two waves and when they are in phase, they amplify each other. When they are in antiphase, they cancel each other. The constructive and destructive interference respectively. An interface between two materials reflects the light. It's caused by a step in the refraction index. Can we avoid the reflection? At first it looks like no, but actually there is a way to get rid of reflection totally, 100%. For example, we can take something really reflective, diamond. It typically reflects up to 17% of the visible light. And the reflection surely occurs on the interface with the air. Intensity of the reflection is given by simply difference of the refractive indexes and incidence angle, so-called Fresnel law. And can we really fool it? The answer is surely yes. And I already gave you a hint, for this we will use interference. That's counterintuitive, but we have to add an extra layer. From the first look, it looks like we will add an extra interface, so the reflection will double, but everything is not that easy. We have to design the scene layer this way. The reflection from the first interface and the reflection from the second interface will interfere destructively. There is no reflection. So we have to align its path. And secondary, we have to align the amplitudes of reflection from the first interface and from the second interface. And it's quite easy. Simple math. This layer is so-called anti-reflectional coating. You can read on Wikipedia. But we are interested in the physics beyond. There is a way to pass through an interface without any reflection. And there is a reversal approach. We can construct periodic structures this way. The propagating wave will be stopped. There will be only reflection. And it's called Bragg mirror. Bragg mirrors can be of the highest quality. It can reflect up to 99 point blah blah blah, many nines, at least 99.9 or something like that. It's easy, achievable, and moreover it's commercially available. Based on those principles, we can generalize it to something more interesting, to a brilliant of physics. It can be generalized this way. If there is a periodic structure, there is a certain wavelength or frequency which can propagate through without any perturbation, 100% transparent for this wavelength, and vice versa. There are bands which cannot propagate through periodic structure. They are known as stop bands. And it works exactly as I told you. From each the period you have tiny reflection, which can be constructive or destructive. And it ends up with such general law. That's how formed bands and band gaps in the semiconductors. Electron is a wave and it's propagating through a periodic media of crystal. There are wavelengths which cannot propagate through the crystal, and there are wavelengths which can propagate through a crystal without any reflection. According to the theorem I told you. As you remember, wavelength is proportional to the energy, so there are some energies which electron can't have, and there are some energies which electron cannot have in the crystal. Such approach explaining band structure of semiconductor is called nearly free electron approach. That's actually the second way to explain band structure. First, says that the band structure originates from the atomic levels. A nearly free electron approach says it's a result of diffraction of the electrons on the crystal. Both explanations are good but applicable for different cases. Now let's have a look how it actually works. I did an example for you. If this video gets 100,000 views, I will make a mechanical prototype. But now I will show you only model, very soft model. But please like the video, write please make a model, then the video gets 100,000 views and I will make it for you. And many thanks in advance. I don't want to make a comprehensive model of the crystal. I want to demonstrate this principle, and it is already seen in a simple one-dimensional array of oscillators. The model consists of 22 waves on a solid rod. The rod is needed to keep all the waves on a straight line, so the model is actually one-dimensional. There are also springs between the waves, but I am not that good in Blender, so I did not show them. It must look samely as I shown you before, but surely in one dimension. The only thing you have to keep in mind, you need not only oscillators, but interfaces between them. If we did it in optics, we would have to modulate refractive index, because as you remember, step in refractive index gives you reflection. But in case of oscillators, you need change of way of oscillators. It's so-called impedance. When there is a step, it reflects the wave. So we will make a periodic structure of some waves. Let's make an array of oscillators, which way is alternating, but the strength of the springs is the same. That's just the easiest model to explain. As much oscillators we have, as closer we are to the infinite crystal, but we need at least 15 to make the simulation quite fair. Otherwise, boundary condition would make too high perturbation and we will not see effect itself. Now I will tiny shake the first oscillator and we will see how all the net is shaking. So they are interconnected, they feel each other. Here we have a nearly philosophical question how to define transparency. I suggest this way. So when I shake first and the last one shakes, it's transparent. When I shake the first and the last one remains still, the material is untransparent for this strain wave. When I simply kick it, we see everything shakes. But what happens when I apply a certain frequency? To make this experiment somehow feasible, somehow makeable, I'm going to make it in the future, I have chosen the following waves and the spring constants. So I expect to have the transparency band and the reflection band somehow in a range of some hertz, just a few periods a second. Let's see what do we have. For instance, I have chosen 8 Hz, and we clearly see, if I shake the first, the last one shakes a lot, just a lot. All the energy is propagating through the chain. If I shake it with a frequency of 8 Hz, I clearly see that all the waves are propagating through the chain. So it's kind of transparency band. But if we raise frequency from 8 to 11 Hz, it looks totally different. Those waves do not propagate, the last oscillators remain still, so we have got band gap in a chain of mechanical oscillators. Wonderful! Just compare how magnificent it looks like. The upper oscillator have frequency of 8 Hz and the chain is transparent. And the lower chain is driven by the frequency of 11 Hz. The last oscillators remain still. Just compare. Wonderful! You can say you are applying too high frequency and all this chain is working as a low pass filter. And it's not true. If I raise frequency from 8 to 14, it's transparent again. It clearly has a band gap in frequency range. For you I did some extra work. I measured the transmission coefficient for different frequencies. I defined it as amplitude of the first relatively to the last. And there are some peaks of transmission and there is a clear band gap, which is amazing. Again, we have got band gap on the system of oscillators. Magnificent, unbelievable. So we quasi explain band gap structure of semiconductor on oscillators, on mechanical oscillators. Dear colleagues, if I told something wrong, please correct me in the comments and I will pin your comment. I am sorry, I'm not theoretician. So, what will be take-home message? First of all, interference is really powerful. With help of interference, we can get antireflectional coating. Secondary, if we have a periodic structure, some frequencies can propagate with no reflection. And that's magnificent. That's broadly used in crystallography, or if we somehow crystallize proteins, it allows us also define structure of the protein. It's very complicated work, but it's feasible. We are getting high reflection mirrors, so-called dielectric mirrors, and eventually band structure of semiconductors. And everything here is based on the Bragg's law. I guess it's amazing. Please like this video if you did not know that this simple mathematical law is excellent, it's brilliant, it's so powerful. Like this video, please subscribe for my channel if you want more videos like this, and please share this video with the friends who can find this video interesting. Thank you for watching and see you in the next videos.